we will be ending on a high note by having Lalitha Vadlamani give us a talk on maximally recoverable codes. Lalitha is from the International Institute of Information Technology at Hyderabad. But before she gives her talk, I want to take a minute to thank the staff at Simons, Omid, who's been very helpful with also other people at Simons, Francis, and others who have helped us with the website and various logistics related to the workshop. They're not here, but I think we should take time.
So again, happy Women's Day. And yeah, thanks Henry and Krishna. Really pleasure to be here. And I'm going to talk about maximally recoverable codes. I think I've been working on this. Work started back in Microsoft Research, but then later, after I joined Reply-T, also I've been working with my student. But the way I want to kind of pitch this talk is that get to the open problems in general. So I'll give a whole lot of background, perhaps only flash my results, but then kind of say where is the gap and what are the open problems in some sense. So that is so that it is more interesting for you. The motivation for maximally recoverable codes is from distributed storage systems. So here I'm saying a node is a failure domain. So there are multiple ways you can talk about distributed storage systems, and there can be different failure domains. For example, nodes are one, but the other thing also you could talk about are disks in general, right? So there is redundancy in the disks, and there is redundancy at node level also. And for the purpose of this talk, I'll assume that node is a failure domain. And whenever we are designing a code, we want to place code blocks or code symbols in different failure domains, so that there's no point kind of placing two symbols or blocks in the same failure domain, because both of them will be lost if that node is down, right? So in distributed storage systems, there are two kinds of failures that you can talk about, and that kind of motivates the parameters for which we want to design systems for. One are permanent failures. Okay, so these are like catastrophic in some sense, right? So which are rare but can happen. You have to account for them. And the second one are temporary failures, which is like power outage, software upgrade, and these kind of things which happen more regularly, but then they are not catastrophic. So which means that the number of nodes which fail maybe like are much lesser as compared to the catastrophic failures that we are designing systems for, right? So in that context, the single node repair became very important. Because of course I'm not motivating repetition, going from repetition to MDS codes is kind of understood. We get a whole lot of storage overhead advantage by going to MDS codes. But then if you want to do a single node repair using MDS codes, this is an example of an MDS code which is taking 10 data blocks or symbols. So there is, when I say symbol, it's at one level of abstraction. Data blocks are what are actually physical in some sense. And then encode it into, so these are 10, and I'm just adding 4 parities, and this is, let's say, an MDS code. And even if, let's say, one fails, the naive strategy is to contact all the 10 other nodes, download 10 code symbols and or blocks, and reconstruct the entire data file, and as part of that reconstruct one, okay, which is wasteful. And when the temporary failures occur, I think what do you say, the the parameter that you want to keep in mind is that somebody is asking you for one chunk of data, and if that one is not available, you want to quickly reconstruct it and give it back to whoever is asking for it. Okay, so this is called reconstruction read in the systems terminology, and you want to do it as fast as possible. Keep the reconstruction read times low, right? So in that sense, it makes sense to somehow decrease it whenever we have one erasure in some sense. Okay, so that is where the LRCs come into picture. And the easiest examples of LRCs, if you want to think about them, is that you think about the previous MDS code that I have shown you, right, which had 10 data symbols and 4 parities. But then take the first parity and split it into 2 parities. Okay, So where this P11 is a function of the first 5, linear combination of the first 5, and P12 is a linear combination of the next 5. And this clearly has a locality, or the number of nodes that you want to connect to has decreased. It has become 5 from 10. Okay. What you have lost is actually minimum distance, in which I will, so all this we will just look at in terms of more general code parameters. This is, so all the references are at the end, and they are just abbreviations here. So, but this is the first work on locality in some sense by Gopalan et al., who have considered a linear code with parameters nk daemon, and now I impose this additional condition that every symbol, in some sense, I need to be able to recover it by contacting our other nodes, right, or our other symbols. So what this kind of says is that Ci is a function of our other code symbols. And a code itself is said to have information locality R if every message symbol, each of the k message symbols has locality R. And they have derived a very nice storage versus locality trade-off in this. So if I have an n, k, daemon code with information locality R, then you have the singleton bound, but then you pay a penalty because of this locality constraint. Okay. The proof is quite nice, and I think it is, I kind of do it in the classes as well because it is quite informative in some sense, and clearly not so intuitive directly, right? So, okay. So what I will, so this part, I'm kind of looking at a code which is a locally repairable code. Here, what I have is that I have 10 data symbols. And the way to look at it is this P1, P2 are what are called global parities in some sense. Okay. And this Q1, Q2, Q3 are the local parities. And this is an example of what I will call it an all symbol locality code, in which even the parities have locality. And so in the previous case, when I told the bound was derived for information locality, which means the message symbols had locality. But then you could also consider the case where the parity symbols also have locality, right? So this is an instance of that. And I am going to talk about topology associated with locality constraints by saying that in the parity check matrix of my code, I should have parities which are supported on, let's say, 5 symbols, right? So that is what I call it as a topology, topology of the code in some sense, or LRC topology means that there should be such local, such parities in my code, right? So, and these are the parameters. I am, right now I'll not just go through them so much in detail, but what I want to emphasize is this topology. So between topology and the code, what is missing is that what am I, putting as entries in that matrix. So that is kind of flexible. So when I say LRC topology, I have not given you what are the coefficients. I'm just saying they have to be supported in these locations, but what you fill it with, it's still, flexible in some sense, right? Okay. So what are maximally recoverable codes? So we saw from the storage distance trade-off that you cannot actually go up to the singleton bound. You're losing in terms of minimum distance, right? But then in general, whenever you look at codes, minimum distance is kind of the worst case, thing which is affecting the erasure capability in some sense. And many times you will be able to correct many erasure patterns which are even beyond the minimum distance of the code, right? So in MDS codes, that is kind of uniform in some sense. But then because there are locality constraints or constraints of some form, there is hope to correct erasures even beyond the minimum distance of the code, right? So that is what we want to correct. What will that affect is that, of course, the minimum distance will not improve. But then when I talked about permanent failures, right? So generally, the way permanent failures is characterized is in terms of some form of a Markov chain and a mean time to data loss. Okay, and in that mean time to data loss, every erasure pattern which you can recover kind of counts towards your advantage. Okay, so it is, if you can correct more erasure patterns beyond minimum distance, still your mean time to data loss will somehow improve. It's not, it's just not minimum distance which is going to kill you, right? And that is the reason why maximally recoverable codes are interesting in the context of distributed storage, because it's not the minimum distance that we are designing for, but some other thing which, let's say, depends on all possible erasure patterns which you can correct. And it is of importance to correct erasure patterns beyond the minimum distance also, right? So what is an MRC? So the way to think about it is that if I am given an LRC topology specified by parameters, let's say n, r, and a few others, right? Then I'm asking what are the maximal number of patterns which I can correct. Okay. So if a code can correct all possible patterns which are information theoretically correctable in some sense, so we call it maximally recoverable for that topology. Okay. What is an example for that? Oh, by the way, so the just thing is that MRCs are, I mean, an instance of MRCs is actually already being used in Azure. Okay. So very well motivated in some sense, right? So if you look at the previous topology, so the minimum distance I think is, so dmin minus 1 is, I think any 4 patterns can be corrected, right? But here if you see, so there are 5 patterns. On the left hand side, if you see, there is a set of pattern which you can correct. Okay. So the reason I'm saying you can correct is because actually these, every parity will contribute to correcting the 5 erasures in some sense. Okay. But there is a set of 5 on the right hand side which you cannot correct, and this you cannot correct irrespective of what coefficients you choose for this P1, P2, Q1, Q2, Q3. So you are allowed to choose coefficients however you want, but this is a pattern which you cannot correct irrespective of how best you can choose your coefficients. Okay. So these kind of patterns, I'll call them uncorrectable. I mean, you cannot correct them under the LRC topology. This topology, you cannot correct them with any coefficients. But on the left, there is a pattern which can be corrected, right? So now we are asking, is that, does there exist a code which will correct all possible patterns which fall in this left category in some sense, right? Okay. So in this context, in the maximally recoverable codes, the questions of interest are, one, what are all the set of erasure patterns you can correct when a topology is given to you? Second, are there explicit constructions of an MRC? Over high field sizes, you can argue that they will always exist. Over low field sizes is of interest. And third, are there lower bounds on the field size of an MRC itself for a given topology? So for this particular topology, which I have been flashing before, the correctable erasure patterns are that, so you puncture the code in one coordinate in each local group. So this, each row here is called a local group. So you puncture the code, one in each local group, and whatever code remains, that has to be a k plus h comma k MDS code. K is the dimension, h is what is called the number of global parities, which in this case is 2. Okay. So after puncturing, you are asking for some MDS code. But MDS code just means that among those k plus h, right, I can correct any h erasures, right? So what are all the erasure patterns you can correct for this topology? You pick one, I mean, you kind of puncture one coordinate per local group, and in the remaining, you drop erasures anywhere, 2 of them, right? And these are all the erasure patterns which can be corrected by this topology. Okay, so it can be exactly characterized what they are, right? So this topology that way is nice in the sense you can at least know what are all the erasure patterns which can be corrected. Now, does there exist a code which does this, right? So by the way, MRCs also go by the name partial MDS codes. And it is mainly from the solid state drive community. And they also have a variant of MRC where you can say that I have disks and I have sectors. And in this subclass of codes, which are called sector disk codes, you're only puncturing in one particular coordinate. I mean, there is an alignment in some sense. I'm not picking arbitrarily coordinates from each row, but I'm only saying that in, I mean, all of them, if they are in a particular column, that has to be corrected in some sense. Okay, so SD codes are a relaxation of partial MDS codes in some sense. Okay, but this is just to, so but there is, I mean, the way I want to look at it is that MRCs if you see, they are applicable for any topology also. But the way partial MDS codes are defined, I think they have not defined it such that they allow for any topology. So there is one difference between the two. Okay? So to construct a, let's say, an MRC, we need to, I think the first constructions again came by Gopalan et al. But they require this thing about k-wise independence. So consider a FQ to the M, extension field of FQ, and a set S is said to be k-wise independent if you pick any set of size k, it is independent over the base field, right? So that is what is k-wise independence. And there is a lemma which just says that these are kind of what are called Murray matrices. These are like your Reed-Solomon kind of Van der Monde kind of matrices, but q powers, right? And these kind of matrices, okay, I don't know if yeah. So our form a generator matrix of an MDS code if these elements alpha 1 to alpha n are k-wise linearly independent over the base field, right? So this is quite easy to prove. So now the construction is, so if you see in the MRC topology, I have said you have to puncture coordinates, right? So the puncturing in the generator domain in some sense is shortening in the parity check domain, right? So if you want to look at, because we'll be designing the parity check matrices, the way to look at it is that, so this is the parity check matrix of interest. This is what is the code, or I mean parity check matrix, and it has to satisfy a certain k-wise independence property. And why is that? Because, so let's say I'm puncturing in 1 and r plus 2, right? So that is equivalent to shortening in this domain, right? Shortening in the parity check matrix, but the shortened matrix actually looks like this. Okay, so I have, you know, kind of zeroed out the columns in some sense, and because this, so the way to look at it is alpha 1, so alpha 2 minus alpha 1, and then I'm multiplying by these, but these are nothing but alpha 2 minus alpha 1 to the power q, okay, because q is a characteristic in some sense. So it still looks like a Murray matrix, right? But with differences of elements, okay? So this will be like full rank, or actually it forms a parity check matrix of an MDS code if all these are, you know, k-wise linearly independent or h-wise linearly independent here. But then this differences being h-wise linearly independent requires that the individual elements themselves, if they are two h-wise linearly independent, then this becomes h-wise linearly independent. Okay? The other way, it's not a necessary and sufficient condition. But then if alpha 1 to alpha n are 2 h-wise linearly independent, then these differences will be h-wise linearly independent. And these matrices form the, you know, parity check matrix of an MDS code. So I'm using a whole lot of things, shortening, puncturing, you know, dual of an MDS is MDS, all these things I am using left and right here actually, yeah. Okay, so but this is the construction, and it has some field size. But so that's a basic construction to keep in mind, and then I can give you a summary of whole lot of constructions which come in, right? So codes with locality, so they have, in general, I would classify the constructions into generator matrix based and parity check matrix based. So in the generator matrix based also you can use Gabardelian codes or linearized polynomials, right? I mean whatever I was telling in some sense. And then another class of codes which kind of came up like around 2019 and so on, which got used, are linearized Reed-Solomon codes. So these linearized Reed-Solomon codes are what are MDS codes, I mean equivalent of MDS codes in what is known as sum rank metric. Okay? And the way to look at sum rank metric is that it kind of unifies the Hamming metric and the rank metric in one, you know, under one umbrella in some sense. So you can pick some parameters in sum rank metric to make it a Hamming metric, pick some other parameters and it will become a rank metric, right? But these codes are, I mean, if you design the codes with locality over these codes, I mean, by generator matrices of the Reed-Solomon codes in some sense, the field sizes will improve, strictly improve as compared to if you are designing using the linearized polynomials. And the parity check matrix approach, you can exactly do the same thing. I have Gabardelian codes, linearized Reed-Solomon codes. There are, even in the parity check matrix approach, you can kind of design them based on linearized polynomials or linearized Reed-Solomon codes in some sense. And the difference between these two approaches, the way I want to think about it, is the way we think about MDS. So when is it easy to design an MDS code from generator matrix? So I would say if it is low rate, when the k is small, right? So that is when I think that it's easy to design in generator matrix. But then if k is very large, then it's easy to do the parity check matrix. Not the Reed-Solomon codes, but in general, if you want to design them. The same kind of analogy you can apply here. When is it easy to design something in a parity check matrix approach is when your code rate is very high. Okay? But if the code rate is very low, then you can still go to generator matrix approach and it gives. So when I say it gives advantages, the field size is better if you do it that way, right? But because in storage codes, we generally use high rate codes, it's good to use parity check matrix approach. Means design the parity check matrices of these codes. Okay. So this is the state of the art and the kind of open problems that I want to kind of say. Here the parameters are slightly different because, just to keep it consistent with this notation, n is the length of the code, r is the length of your local group, h is the number of global parities, q is the field size, and a is the number of local parities. So the way, so there's a lower bound on the field size, which kind of says it is, linear in n, but there is an r which also can grow with n. Maybe it's not growing linearly with n, but it can grow in any way. So, but what are constants here in general are the number of local parities and the number of global parities. We want to kind of keep them as order of 1. Right? N is growing, maybe k is growing, even the number of local groups is growing. But then the number of local parities and the number of global parities, we want to keep them constant. So here in this case, it is A and H. Okay, so those things we want to keep them constant. So here it's still, linear in n and some power of r, whereas the upper bounds on the field size, many of which are like linearized Reed-Solomon based constructions, you can see it is max of n over r power r minus a, and there is still a huge gap between the upper and lower bounds on the field size, and it is not known how to get better constructions. So it is a very good open problem in some sense in this area, right? So one connection which I would like to mention is a matroid connection, which I was excited about some time back, assuming that maybe it will give me lower bounds on the field size. Yes. Global.
H is the global. Right?
Yes, A is the local parities.
So maybe it's a very silly question, but like R is the size of the
local group, and so it is like.
Suppose I don't have the local group constraint.
Mm-hmm.
Then I know that I can have polynomial field size, right?
Mm-hmm.
Right. So, but it seems like it is then going to be some power of. Because if R, so then my R is equal to n.
Mm-hmm.
So as if the field size is growing when I'm getting rid of the local constraint.
Oh, but okay, wait a minute. So
Would A be 0 on that?
It's the min, right?
A goes to 0.
I say
A is the min.
because A is the number of local. Okay, so A will also be 0, and therefore it will just be
yeah, sorry, I think I missed you, but yeah. So this matroid connection was interesting to me, assuming because at that time there was no lower bound on the field size yet. But the thing is, the punchline is that so if you are given an LRC topology, right, and I have an MRC for that topology, you can exactly specify the matroid for that code. And what is meant by matroid? Don't forget about the actual definition of the matroid. But what matroid just means is that what is the independence and dependence relations of columns of your generator matrix. That's all, right? So this can be exactly specified if you are told that I have an MRC with a certain topology. Okay? But the same thing cannot be exactly specified if you are just said, I have an LRC for that topology. That is not known. Okay? So I thought this connection would be interesting to derive bounds on the field size because there are many matroid invariants of a code which you can immediately write down. So once I said I have MRC of a certain topology, and then I know what are the weight enumerators, I know what are the generalized Hamming weights, all those things I can exactly specify. And I was trying to derive a bound on the field size, assuming the weight enumerators have to be positive. So you can actually derive bounds on the field size of MDS codes, saying my weight enumerator has to be a positive number. But here it turns out I don't get, the previous kind of nice bounds. It turns out to be very linear kind of bounds, and they're not, not very interesting. So that was a disappointment in some sense. But the connection is something which I like, and that's why I wanted to talk about it. And my work mostly has been on extending this MRCs, constructions, field size bounds, and everything to what is called hierarchical locality, where you are saying I have two levels of locality, right? So in the sense I have, so I can just show you the parities matrix. The parities matrix looks like this. So there are some local parities, there are some mid-level parities, and there are some global parities. So this is two levels of hierarchy. So whether it is practical or not, so if you are increasing your code size quite a bit, right, and if your K is quite a bit, then this definitely makes sense. And I think I have kind of come across some companies which are interested in hierarchical locality also. So that much I leave at that. And what is the trick behind doing this MRCs for hierarchical locality is that you pick the local parities from the base field. Yeah. So the way to look at it is that, see, if I am somehow kind of exceeding the whatever local parities give me, now again I have to go to K, right? So suppose if I say I have R1, which is for the local code, but then I have a bigger local code or a mid code, which is R2, and then K, right? So there is two stages of locality. So once you, kind of cross the number of erasures in this, you can go to the mid-level code, try to kind of, repair from that. And only if you cross the minimum distance for that also, then you go to all the K symbols, right? Sorry? Yes, you lose minimum distance. Yes. So that is a flexibility. I think we want, if we are actually going to larger and larger codes in some sense. Yes, that's correct. So, so the way this is constructed is that the local parities you pick from a base field, the mid-level parities you pick from an intermediate field, and the global parities you pick from a extension of that. And then kind of get this 2H-wise independence kind of things, two level again. Okay? And then we have shown that this actually is a code with MRC with hierarchical locality. Okay? So, okay. I think 5 minutes is a lot. So again, I just want to convey the main principles here. Actually, this is perhaps, one universal construction in some sense, but we have a lot more constructions and field size bounds and all that. So, but just the principle is what I want to convey, right? So the next interesting topology, which I think, again, came from Sergey Khanin, Shivkant Gopi and group, I think, yeah. So is a product topology, right? Where, you have, there are row codes and column codes, right? And the code word is arranged as a matrix. Each row is a code word of this, each column is a code word of this. What is very interesting about product topology is that you cannot even kind of specify what are all the correctable erasure patterns in this. It's not possible, okay? And what they have done in their paper is that for one, if you make one of these A equal to 1, means either row code or column code is a simple parity check code in some sense, then we can specify the erasure patterns. But if you make A equal to 2, B equal to 2, not known. Even, I think this has been there for 4 or 5 years now, but it becomes an extremely hard combinatorial problem. It's not even clear what the erasure patterns are which can be corrected. Okay? So for the case of A equal to 1, they had a proof, and we had a nice alternative way to look at it. I'll just look at that. So if you have an erasure pattern here, so you can draw a graph based on the erasure pattern, in the sense that you can kind of match the erasures with non-erasures from a parity row, and kind of say that whatever has been erased in one of the top rows can be recovered from the parity in the bottom row which is not erased. Okay, so if there is so we kind of make a graph from this and try to say if there is a matching here, then that erasure pattern can be corrected, otherwise not. Okay? So this is just an alternate formulation of the proof that they had, but I thought this had much more intuition to understand the erasure patterns in some sense. And this applies for any A and B, but the thing is, even though this matching condition is there for higher A and B, the problem what comes when you go to bigger matrices is that there are dependent elements in a matrix, in the sense that all the entries are not like you can pick them independently from some high field and all that. So those kind of arguments break down. So still we cannot show that those many erasure patterns can be corrected. So but the matching condition I think is kind of very intuitive. And in the community itself, what has been the major breakthroughs is that I think Brackensek, Gopi, and Makam, so they showed that for the case of A equal to 1, for which we know what are all the erasure patterns which can be corrected. Okay, so you know that one of the codes is still a parity check code. What about the other code? So suppose if I say for this topology it has to be an MR, what is the other code? So that other code turns out to be an higher order MDS code. Okay, a very interesting generalization of an MDS code. Okay. It's hard for me to state, but I'll be happy to chat offline what the definition of a higher order MDS code is. But so this is what they have proved. And also another very interesting connection which they have made is that the duals of these higher order MDS codes are optimal list decodable codes, optimal combinatorially list decodable codes. So these two connections they have made in their paper. And a major open problem is that, so this higher order generalization of MDS codes, we don't know any good constructions at all. So that is a major open problem in the area. Okay? So I'll stop there. I have a lot of references. I'll be happy to share slides. Yeah.
Yes, Jamila.
So can you explain again, what was the problem from the Matroid point of view when you tried to get some field size bounds? Were you trying to look for some forbidden minors, or like what were you trying to do with Matroids for the field size?
Oh no, so based on matroids, you get the weight enumerators exactly, right? So I just wanted to get a bound on the field size by saying that AW, okay, is greater than or equal to 0. Okay, so that kind of gets me a bound on the field size, but that bound was not anything interesting, in the sense that it was not what the constructions or anything were showing, because I was expecting either an n square kind of a bound or something like that, right?
Okay. Yeah. But could you maybe get some kind of a bound by finding, at least like upper bound by finding some bad minors in your Matroid?
Possible. Yeah. I mean, actually, I have not tried it after that. But one good thing is that this is, even the matroid connection kind of is applicable to any topology also. I mean, I have made only for LRC as if that is for that, but it is applicable to any topology. For LRCs, yes, you can even look at bad minors and all that. I have looked at your paper actually, yeah.
Okay, but maybe we can talk more.
Sure. Yeah.
Well, there is a family of codes called the integrated interleaving.
Right.
Their correctable patterns are pretty clear.
Mm-hmm.
They have low alphabet sizes. So why aren't they a good alternative to all those hard constructions?
So it is, are they, I mean, maybe they are, if they are not, I mean, if we are not imposing the condition of maximal recoverability, let's say, right? So then I think, at least for LRCs, we know Tamo bar codes, which are linear field size in some sense, right?
Lower alphabet size than LRCs.
Right.
And also they correct more patterns than LRCs.
Okay. So maybe except for the minimum distance, maybe.
They are not
Yeah.
optimal LRCs.
Yes.
Average correction.
Yes.
So you should check them out.
I think, yeah, I have partially looked at them, but I think I need to check more. Yes.
I mean, if you say that they correct more error patterns, that's exactly what we don't want in the maximally recoverable code, right? Or am I misunderstanding something?
No, you want to correct more erasure patterns, just that we want to correct all possible d-min also. So we want them to be optimal in terms of minimum distance as well, right? So.
But I mean, the reason why the Tamo-Bar codes, for example, are not MRCs, that's because they have too many dependencies.
Yes.
So in some sense, they can correct things that.
No, but he's talking about codes which are maybe not even LRCs in some sense. Yeah. So they are not optimal LRCs. So that is, yeah.
Oh, yeah, go ahead.
Sorry, maybe I should. So higher order MDS, I thought first that you mean just the genus larger than 0.
Sorry?
So by higher order MDS, you don't mean algebraic geometry codes, you mean something else.
No, they are something else. So actually, you look at, so the way I look at it is that, you know, I pick a random matrix over real numbers, let's say, right? So, and I look at all the possible intersection dimensions or union dimensions and so on, right? So if my code has, you know, intersection and union dimensions given by, let's say, a matrix over real numbers in some sense, so that is higher order MDS for me. And those intersections, etc., how many sets we are picking, that kind of determines what is the order.
Okay.
So what you can say is that actually if you pick that order equal to 2, you can get back to MDS definition itself, right? But if you pick order equal to 3, they become highly non-trivial. Any RS code will not satisfy that property, and they are higher order MDS. Yeah. So, but just that the way to think about it is you go to high enough field and try to look at the intersections of arbitrary sets of columns in the generator matrix in some sense.
Yeah, is it okay?
Yes, yes.
So I'm intrigued about the generalized anyway. So you basically try to find the smallest support of
Yes.
a pair triple, and
Yes.
that failed as well.
Yes, you can do that because for in MRCs, right, the way I look at it is that there are so many punctured MDS codes. Okay, so other than what, so for MDS codes, what you can say is that I am filling the generalized Hamming waves from the other side. I mean, I'm filling the highest weight at n, the next highest weight at 1 less than that, and so on, because there are no constraints, right? So, but for these codes, it is like I'll keep filling that, but at some point I have to leave a gap for the locality, because the support sizes, right? If I pick a 2-dimensional code, I'll just get that into R+2 in some sense, right? So yeah.
All right, that brings us to the end of the workshop. Let's thank